We'll get started. So we were discussing augmented Lagrangian method. And remember, the augmented Lagrangian is defined as f of x plus lambda transpose h of x plus c over 2 norm of hx square. And one of the methods that we talked about towards the end of previous lecture is if we have this following update, xk plus 1 equals to argmin lck x lambda k, x is in Rn, and lambda k plus 1 equals lambda k plus c h of xk. So what we had said was, if you have this sort of update scheme, then this lambda k actually converges to lambda star under certain conditions, okay, which satisfies the first order necessary condition for optimality. Now, of course, we need to, what the note at which we ended was, we need to check for second order sufficiency condition in order to ensure that what we have converged to is an optimal solution or not. But what actually this gives us is an algorithmic method to update lambda k. So remember, in the original augmented Lagrangian method, we had to pick some lambda k. It need not be updated in a specific fashion. But it turns out that if we update it in this particular fashion, we have some desirable properties of the algorithm, and this algorithm is known as method of multipliers. Okay, and the property of this method of multipliers is that this particular sequence converges to lambda star, which is the Lagrange multiplier. Now, of course, there is a general result and then there is a specific application. So in the general result, lambda star and x star satisfies necessary first order necessary condition for optimality. In reality, in most of the applications that you might be interested in, most likely this lambda star would be the Lagrange multiplier for the specific problem. Okay, so this method of multipliers was extremely famous in 2010 to 2018ish for a variety of reasons. So a lot of people were investigating variations of method of multiplier algorithms, and in fact, one of the assignment problems that I've given to you, I've changed the method of multipliers a little bit, and I've asked you to prove the convergence of this algorithm. So in order to understand how to solve the problem in the homework, let me try to give you an example here in the class, so that way you will try to figure out how to solve the homework problem. I'm trying to pull up that example. Okay, perfect. So I want to apply this algorithm to a simple problem. So I want to minimize x1 square plus x2 square such that x1 is equal to 1. What's the optimal solution here? What is x1 star, x2 star? Can you solve it by hand? Is it possible to solve this problem by hand? What is the solution?
1-0.
1-0? Perfect. Let's apply this algorithm. So let's write down what the LC of x comma lambda looks like. So let me write it as x1 minus 1 equals to 0. So it is in the hx equals to 0 format. So I have half of x1 square plus x2 square plus lambda times x1 minus 1 plus c over 2 x1 minus 1 square. Is this a convex function of x? So quadratic function, linear, quadratic, convex function. Okay. So what is the argmin over R2? I just have to take the first derivative, set it equal to 0, and I get xk. So my x argmin, well, let me say what's the gradient of LC. What is the gradient? x1 plus lambda plus c x1 minus 1. Did I do it correctly? And then x2, that's it. So gradient of x LC x lambda equals to 0 implies x1 is equal to c minus lambda over 1 plus c, x2 equals to 0. Did I do it correctly? Yes.
We need to consider when x1 minus 1 is less than 0, and we need to absolute value.
No, you don't need the absolute value. So if you take the second derivative of this, it's equal to 2. Of x1 minus 1 square, the second derivative is equal to 2. So it's always greater than equal to 0. Right? Yeah. And c is a positive number. Did I mention that c is a positive? Yeah, c goes to infinity. So c is always greater than 0 in augmented Lagrangian. You're never considering c less than 0. Okay, so this is the argmin of LC of x lambda. So what's my xk plus 1? Xk plus 1 equals to ck minus lambda k over 1 plus lambda k and 0. What's my lambda k plus 1? Lambda k plus ck h of xk. So h of xk is let me confirm something. Okay, I apologize. This is xk. So not xk plus 1, this is xk in the method of multiplier. Can you make that correction? This is xk is equal to argmin of LC. So this is my xk. lambda k plus ck minus lambda k over 1 plus lambda k minus 1 1 plus ck 1 plus ck. This is not lambda k. What do I get? Minus lambda k minus 1 over 1 plus ck. Have I made any mistakes? So this would be equal to lambda k minus ck over 1 plus ck. This is my lambda k plus 1. Does this sequence converge? If I pick ck going to infinity, let's pick a simple example. So if my ck is constant, ck equals to c, my lambda k plus 1 is written by 1 plus 1 over c lambda k minus c over 1 plus c. Does this iteration converge? Why or why not? xk plus lambda k plus 1 is something less than 1 multiplied by lambda k minus some constant. Does this sequence converge? No? Let's do proof by consensus. How many of you think that this sequence converges? How many of you think this sequence doesn't converge? 1, 2. Are you voting yes or no? You're abstaining from the vote. So here is a population which abstains from voting on matters of national importance. Yeah.
When you say like, what do you mean? Like, doesn't it just go to -1? Like if C approaches infinity?
If C approaches infinity, this one goes to -1. That's right. You are right. But the question is, would this update converge or not? So that's the limiting argument. You're taking the limit C goes to infinity. This thing seems to converge to -1, and that's completely right. But my question is slightly different. My question is, does this sequence converge or not? So if I'm updating some sequence like this, would it converge? Yeah.
I think if C is 0, then it converges properly.
C is 0, then lambda k doesn't get updated at all. But C has to be greater than 0.
And the remainder like C smaller, like the C over 1 plus C.
Uh-huh.
So like maybe the first term goes to 0, but the remaining is the second term.
Okay. Okay. So
Okay, it will converge to 0, right?
it'll converge to 0. So one person is saying that this should be converging to -1.
Yeah, when C goes to infinity, it will be -1. But right now we are always, how can I say, multiplied by something more than 1, so it will needs to go to 0.
Yes. So this term is trying to push it to 0, but this one is trying to push it to a negative value. Right? So, okay. So, yeah.
Does C change in value or does it stay the same value?
So right now I'm assuming that C is not changing value, just for simplicity, because I want to analyze the convergence of the sequence. And then I'll let CK go to infinity in this next discussion. Anyone else has any thoughts? Okay, so in general, this is a well-known result. If you have a sequence yk plus 1 equals to ayk plus b, and rho of A is less than 1, so the spectral radius of A is less than 1, this implies yk converges to some y bar, and this y bar is equal to 1 minus, sorry, identity minus A inverse B. Okay. So if I have a matrix getting multiplied by a vector, I'm adding some constant to it, some constant vector to it. If my spectral radius of A is less than 1, then this sequence must converge to a limit which is I minus A inverse times B. What's the spectral radius of 1 over 1 plus C? 1 over 1 plus C. It's just a scalar, right? So that's the spectral radius itself. It's less than 1. So this sequence will converge to some lambda star, which is I minus A inverse. So 1 minus 1 over C inverse. So 1 plus C over C times negative C over 1 plus C equals to minus 1, which is what was the limit C go to infinity. It's the same limit. Why should this be the case? Okay, let's try to understand why this is the case. This is something that, by the way, in the homework I have mentioned this particular result. So if you go to your homework 4, this result is there at the beginning of homework 4 that you can use without proving, but I'm going to cover the proof in the class so that way you know why that result holds. Okay, so y0 is given y1 equals to a y0 plus b, y2 equals to a y1 plus b equals to a y0 plus b plus b, a square y0 plus ab plus b. What is y3? A times this whole thing plus b. So that's a cube y0 plus a square b plus ab plus b. Do we see a pattern here? There is a pattern. So yk equals a raised to k y0 plus summation a raised to ib. I goes from 0 to k minus 1. Okay, so now we need to analyze the convergence of this particular sequence. What happens to this term as k goes to infinity? So my spectral radius of A is less than 1, rho A is less than 1. What happens to A raised to k times y0? It converges to 0. This term is going to converge to 0. So spectral radius of A is less than 1. It means that it is shrinking y0 at every iteration. So if you shrink it at every iteration by a factor, eventually you will go to 0. What about this term? Okay, so this term seems to be an infinite series. What is this converging to? Summation I equals 0 to infinity a raised to I multiplied by b. What is this sum? I minus a inverse times b. So this is geometric series. So I'm sure you guys have studied geometric series. So if it was a scalar, it is 1 over 1 minus a. But this one is a matrix. So the way you do the geometric series for matrix, you get I minus a inverse. Okay, any questions so far? Okay, so that's what I was mentioning, that this yk is going to converge to y bar, which is 1 minus a inverse b. And that's what gives us this particular result as well. Okay, so this one, what we have essentially proved is that this method of multipliers is going to converge to lambda star equals to -1 for this particular problem. What about xk? So xk converges to what? So xk equals to c minus 1 over, sorry, c minus lambda k over 1 plus c and 0. What is this converging to? This is converging to c minus 1 over 1 plus c0. There seems to be a problem. So lambda k is converging to -1. Oh, yes, I know what the problem is. I have c plus 1 1 0. So lambda k is converging to -1. So I have c plus 1 over 1 plus c, that's equal to 1 0. So xk is converging to x star, lambda k is converging to lambda star for this particular problem. So in the assignment, I have changed the method of multipliers slightly, the formula for method of multipliers, but ultimately this is the result that you are trying to get to. Can someone tell me what happens when rho of A is strictly less than 1 but still very close to 1? So if it is 0.99999, what happens to the convergence? So what happens in those situations is if this value is very close to 1, the convergence is going to be very slow. If it is close to 0, the convergence is going to be very fast. Okay, so the convergence speed is a function, how quickly this particular sequence converges is a function of how small or large the value of rho A is. So if rho A is close to 1, if it is 0.999, it's going to take 1 million steps to converge. If rho A is 0.01, it's going to converge in like 10 steps. Okay. So in the assignment, what you will notice is under certain conditions, rho of A is very close to 1, and it's going to take 1 million steps for your algorithm to converge. You will see it in practice, in your simulations. On the other hand, if you pick C carefully, you can have rho A very, very smaller than 1, in which case the iterations will converge very quickly. Now remember, in the original algorithm, we had mentioned that Ck goes to infinity. What happens when Ck goes to infinity? This term becomes closer to 0, and therefore you converge to the value -1 much faster. So you don't have to take Ck going to infinity, you will still converge. But if you let Ck go to infinity, you will converge much faster. You will be able to get to the optimal solution in a fewer number of steps, fewer number of iterations. Okay, when you are implementing these algorithms in actual problems, you have to keep in mind that you want to get to the solution as soon as possible, but you also have to keep in mind the stability of the algorithm. So I've given you an assignment, and you will see how these things appear when you are actually implementing the algorithm, what happens when you pick CK very large versus CK very low. And it will help you appreciate all of these trade-offs that you have to make while implementing these algorithms. Any questions so far on method of multipliers? So let's look at the augmented Lagrangian for problems with inequality constraints as well. If there are no further questions, I'm going to erase this slide. So I want to minimize f of x such that h of x equals to 0, g of x is less than equal to 0. The augmented Lagrangian here is slightly more complicated, but it's given by f of x plus lambda transpose h of x plus c over 2 h of x square Yeah, this looks correct. Okay, so how do we get to this particular expression for augmented Lagrangian? I'll just give you the hint. But before I give you the hint of how to get to this particular expression, I want to draw your attention to the following problem. So I have a problem with inequality constraint. I know how to solve the equality constraint problem. Can someone tell me how can I convert this into an equality constraint problem? So I have x is in Rn. I have a bunch of inequality constraints. I want to convert it to equality constraint. What can I do? So I'm going to add a term zj square to each of the inequality constraint. I'm going to set it equal to 0, and I'm going to add z as a optimization variable in the problem. So I could go from this particular problem to this problem, and they are equivalent problem. Now you can define the augmented Lagrangian for this. X, z, lambda, mu, and then you can do minimize z in RR, and this is going to give you this particular augmented Lagrangian. Okay, so that's the derivation. If you solve this particular, if you compute the augmented Lagrangian here, minimize with respect to z, you will get this particular expression for augmented Lagrangian for this inequality constraint problem. So that's roughly how what the argument is for going from things we already know to things that we don't know. Okay, so I have an inequality constraint problem. I have figured out how to define the augmented Lagrangian method. Now I want to come up with a method of multipliers for this. So here is how you would write the method of multipliers. So my xk is argmin lck x lambda k mu k. X is in Rn. Lambda k plus 1 equals lambda k plus ck h of xk. And the expression for mu k is slightly more complicated. Mu k plus 1 comma j equals to max 0 mu kj plus ck gjxk for all j. So this is the method of multipliers for inequality constraint problem. How would you solve this problem? Argmin of LCK. How will you solve this in actual in a computer? So remember, this is an unconstrained problem. All the stuff we studied for the unconstrained optimization, Newton's method, gradient, steepest descent, Armijos rule, all of that stuff can be applied here in order to solve this particular problem. And then you update the lambdas and mu's and rerun the same optimization problem all over again. And this would converge. Again, in reality, it would converge to a stationary point. Sorry, in mathematically, it will converge to the stationary point. But if you are solving a real world problem, it's quite likely that it'll converge to an optimal solution or a locally optimal solution. Okay. Anything else that I wanted to cover here? We've noticed that the convergence in this particular case, like we had showed in the previous example, you're actually going to converge exponentially fast. Okay, so I know that you have seen a bunch of convergence results so far. So you have seen convergence of Polyak, convergence of Nesterov's method, convergence of steepest descent, figuring out what the right or what the best step size is going to look like for those kind of problems. So remember what is xk minus x star norm if it is in the y-axis and x-axis is iteration k, or I would say log of k. Was it log on the y-axis or log on the x-axis? I think log on the y-axis. It kind of looks like this, right? So it converges very quickly. So that's roughly what the convergence of this particular algorithm is also going to look like, which means that it will converge very quickly to the optimal solution. And depending on the way you are picking CK and you're picking, CK is the only hyperparameter here. So depending on how small or large CK you are picking, you will have faster convergence versus slower convergence. Okay. So that's about method of multipliers. Now the next algorithm is sequential. So we have only two more algorithms left. One is sequential quadratic programming and the second one is Lagrangian method. So let's talk about sequential quadratic programming now. Any questions before I move on to the next topic? Okay. Method of multipliers is extremely useful in wireless systems, by the way. A lot of people use method of multipliers in optimizing, I don't know, rate and throughput and whatnot in wireless systems. I don't know much about it, but I know people in networking area within our department, they tend to use these algorithms quite a lot. Anybody from wireless systems area here? Communications area? No one? Okay. Sequential quadratic programming. Anybody who's coming from control systems area? A few people. Okay, so some of them are working on automotive systems. You might be working in some other maybe chemical systems or whatever. So sequential quadratic programming is heavily used in optimization in sort of control systems. It's not like you can't use these methods, but for whatever reason, somebody picked sequential quadratic programming and then everybody stuck to sequential quadratic programming in that entire area. So anyways, you can use any of the methods we have talked about, but this algorithm is heavily used in control systems to solve a problem. So what's the problem statement here? So again, let's start with a simple problem. I want to minimize f of x such that h of x equals to 0. So I will add the inequality constraints in a bit, but let's talk about this particular problem. What do I know about this problem? So what I know is gradient of x of Lx star lambda star is equal to 0, and I know that h of x star is equal to 0. So we need to find an x star and lambda star that satisfies these two conditions. What should I do? How can I come up with a optimization problem that if I solve, I converge to a point where x star and lambda star satisfies this condition. So let me come up with a naive solution. I'm going to define a penalty function as a function of x and lambda, which is norm of gradient of Lagrangian square plus norm of hx square. This is a penalty function. What happens if you are minimizing? Let's say you are solving I want to minimize over x and lambda p of x comma lambda. Okay, let's say you are solving this problem. What is the optimal solution here? So remember, this is always non-negative because this is norm square, so non-negative. This is norm square, so non-negative. And I know that there is an x star lambda star that satisfies the gradient equals to 0 and hx star equals to 0. So technically, this x star lambda star that we are looking for is an optimal solution to this particular penalty function. Okay, so that's good. I'm looking for an x star lambda star that satisfies this condition, and that x star lambda star seems to also be an optimal solution to this. However, this penalty function may have multiple locally optimal solutions and globally optimal solutions. In particular, there is no guarantee that all x star lambda star of min px lambda would be an optimal solution slash Lagrange multiplier pair. In other words, if I were solving maximum f of x such that h of x equals to 0, even that particular problem will have some x star and lambda star that would satisfy a similar result, and therefore that would also satisfy this particular condition, which means that it will also be a minimum of this particular penalty function. So in other words, let me put it as minus h of x equals to 0. So in other words, there is no point solving this penalty function because it might converge to a local minimum or it might converge to a local maximum. Okay, so this penalty function is not good. That's the argument I'm trying to make. I can construct this penalty function. The minimum point satisfies is an optimal solution to this penalty function, but turns out that maximizing solution is also a solution to this penalty function, and therefore it's of no use. This penalty function is of no use to us. So what's a good penalty function? Okay, so that was the idea. People were thinking about it for quite some time, and here is a penalty function that seems like a good option. So I'm going to minimize f of x plus c p of x. X is in Rn. So this is an unconstrained optimization where p of x is given by max of absolute value of h1 of x, h2 of x, hm of x. Okay, so the penalty function is constructed in the following fashion. I have a whole bunch of equality constraints here. I take the absolute value of each of those equality constraints. I take the maximum of all of these absolute values. I define it a function p of x. I multiply it by a constant c, which should be sufficiently large. And then if I solve this unconstrained problem, minimizing x in Rn, I get an optimal solution. So it turns out that the x star for this is also an x star for this particular problem. Okay, so a local minimum of that is a local minimum of this, a global minimum of that is a global minimum of this. So I'll go over the proof in the next class, but I have some time, so I'll tell you what the theorem is, what the underlying mathematical result is. So this is for the equality constraint case. Let me write down the same thing for the inequality constraints. Where should I write down? Maybe I write down here. P of x equals to max 0 g1 of x gr of x absolute value of h1 of x absolute value of hm of x. This is the penalty function for the inequality constraint case. And the theorem is x star local minimum and regular satisfies second order sufficient conditions C is greater than summation absolute value of lambda I star plus summation mu j star. Then x star is a strict local minimum of fx plus c px. I want to emphasize here that checking that sufficient conditions are met or not is a very difficult challenge, because uh, but uh, but most of the problems that you would be encountering in real life would satisfy those conditions, although we cannot say things more generally. In my personal investigations, I have found that the sufficient conditions are generally satisfied. But this requires, this particular algorithm requires x star to be a local minimum of this problem. Oh, I haven't written the problem with inequality constraint. So min fx h of x equals to 0, g of x less than equals to 0. So I have this problem. X star is a local minimum. X star is a regular point. X star, lambda star, mu star satisfies sufficient conditions for optimality, and C is sufficiently large. So how large should C be? It should be greater than the absolute value of all lambda A star and greater than the sum of mu j star. I mean, all of these terms are added together, and C must be larger than all of these things. So it has to be sufficiently large. Then X star is a strict local minimum of this particular optimization problem. Now the question is, how do we solve this problem? Okay, so we have an optimization problem here which is not differentiable. Okay, look at P of x. So P of x is maximum of a whole bunch of functions and a whole bunch of absolute value of functions. So because there is a maximum operation here and because there is an absolute value here, it becomes non-differentiable. So P of x is non-differentiable. So theoretically, this sounds like a very good result. Practically, I'm asking you to solve a non-differentiable optimization problem. Okay, so how do we solve this particular problem? So let's think about it. How would you solve this problem? So I give you an optimization problem and the objective function seems non-differentiable. What would you do? And let's go back to the first principles. How did we solve an unconstrained optimization problem? At the very beginning. So remember lecture 4, lecture 5 of this class, this course. What did we do to solve an optimization problem, an unconstrained optimization problem? What's a descent direction here? How would we define a descent direction? Any thoughts? So what I want is find D in Rn such that f of x plus d plus c px plus d is less than equal to, not less than equal to, less than f of x plus c p of x. Right? This is what we did in lecture 4. And the reason why we were able to get all of that steepest descent stuff is because if d is small, I can do a Taylor series approximation here and I can find a descent direction d. So in lecture 4 or lecture 5, d was taken to be minus capital D times gradient of fx, where this is a positive definite matrix. And we showed that because of Taylor series approximation, if I pick my d according to this fashion, it satisfies this condition. Okay, so now we need to do the same thing. So in lecture 5, we could do the differentiation and we could show this. Can we show the same result, or can we find a d that solves this particular problem? So this is something we will study in the next class. So we'll do two things in the next class. One is we will try and understand why this condition holds, why this particular thing holds. So we'll spend some time on that, maybe like half of the class. The other half of the class, we'll try to find a d that satisfies this particular inequality, and that would tell us how exactly to solve this minimization problem where we have non-differentiable penalty function. And that would give rise to sequential quadratic programming algorithm. Okay. One of the problem that is still missing, if I don't know what the solution is, how do I know lambda I star and mu j star? And if I don't know what lambda I star and mu j star is, how do I know what value of c to pick? Okay, so that's also an important consideration. So we'll talk about all of these problems in the next class, and we'll complete the discussion on sequential quadratic program. Thank you.